In this video we will look at two figures that further illustrate the uncertainty that we have when we have a Bayesian neural network. So we can visualize this uncertainty in ways in which we cannot do this with a normal neural network. So to generate these figures, we're gonna again use the posterior predictions, but now we're gonna set input not to the value xtrain or xtest, but we're gonna put it equal to the whole grid. So we're gonna ask for a prediction on the whole grid -3 to 3 for both x1 and x2. Yeah, so the input we set to this grid. Then here we're gonna sample. So we sample from the trace. So I've already done this, so we don't need to wait here. So it samples. And now we're going to plot using a color map, a C map. So you can go to so again use SN diverging palette with a question mark to see what it's about, or you can Google it and get more information about it. I'm not going to talk about this. When we do the contour plot, this is where it happens. Here that we set the color map equal to the C map that we've defined here above. So what we're plotting here is now our test data. So again, x test where y test equal to 0, and then the first coordinate, y test equal to 0, the second coordinate. So these are going to be the blue points. Then on top of that we're going to have the red points. And then these contours now are going to be colored. Yeah, so we also have this color bar that you can see here on the right. So now we're going to look at how we can interpret this figure. So this is the code generating the figure. It's very similar to the one above, except that we're using a color map here and we're not just plotting only the 0.5 contour. So this color bar shows what the colors mean. So when it's blue, the probability that y is equal to 1, so the probability that the dot is going to be red, is actually very low. Yeah, so here we predict y equal to 0, or here we predict blue dots. In this part of the figure we predict the red dots, so the probabilities of y being equal to 1 is high, so it's the more red it becomes, the more deeper red it becomes, the more likely it is that y is equal to 1, according to our models, according to our predictions. And as you can see here in this region between 0.45 and 0.6, so where we had our 0.5 contour before, this is where it's very light. So this is this part here, that sort of, there will be most of our 0.5 contours. But it can be, of course, diverge a bit into these other light areas as well. So the thing here is that our predictions here are not based on one set of parameters for our neural network. We actually take the mean over all the samples that we have for our parameters of the neural network, for our weights in the different nodes. So here we look at the average, and later on we're going to look at the standard deviation. Yeah, because I have a whole family of probabilities now, of weights, I can actually generate also the standard deviation of my predictions. Yeah, but here we just focus on the fact that if we get draws around here in the deep blue area, we're pretty sure that y is equal to 0. If we get draws here, we're pretty sure that y is going to be equal to 1. But around here, we're going to have a couple of mistakes. Yeah, so first of all, we're not that sure. And second, there are some dots here, like this one, where y is equal to 1, although it is in blue territory. Yeah, so our prediction would be quite firmly actually that y is equal to 0 here, but that's incorrect for this observation in our test data, because it's actually equal to 1. Yeah, and also here you can see blue dots that are in the red or some sort of a light red area, where we simply predicted incorrectly. Yeah, so what we learn here is that we're surer about some predictions than we are about others. Yeah, so predictions over here we're pretty sure, predictions over here we're pretty sure, but closer to this boundary we're not so sure. And of course the fact that we have this probability here, this is what a normal neural network will tell you as well. Yeah, so here the probability of something being red or blue is close to 0.5, so it's clear that we're uncertain about it. Yeah, but because this is a Bayesian analysis, we can basically go one step further. So what we've done here is we looked at the mean of our probabilities. Yeah, so what comes out of this posterior predictive is the probability that something is, that y is equal to 1, so that the dot is actually red. And we took here the mean across the different samples. But we can also take the standard deviation. Yeah, so this plot is very similar to the one above, so it uses a slightly different color map. So you can look at that, but the main difference is this thing here. So now we look at the standard deviation across the samples. So that says something about how much does this probability vary between the different draws from my posterior distribution. This is something that we cannot do in a normal Bayesian network. In a normal neural network, so non-Bayesian, in a normal neural network, as it would be generated by TensorFlow and Keras. Yeah, because there we don't have this idea of a family of probabilities, so we cannot actually say what the standard deviation is. So as you would expect, the standard deviation here is pretty high, yeah, because we're not so sure whether it's going to be blue or it's going to be red, so we're going to have pretty high standard deviation, and that standard deviation here can actually flip our prediction quite easily. Yeah, so again you see these points here that are misclassified because there is quite high uncertainty about whether y is going to be equal to 1 or equal to 0. But you can also see the very light area, so if we get a point over here, we're very sure that this is going to be blue, and if we have a point over here, we're actually very sure it's going to be red. But for points around here, we're not so sure. And points around here, we're also not so sure, because we can see there are draws from our posterior distribution that would qualify sometimes the point as red and sometimes as blue. So this is the benefit that we get from a Bayesian analysis, that we get this additional uncertainty measure here. And the reason why it's important is that you might want to think of an example like an investment opportunity. And let's say the blue investment opportunities are going to be profitable with very high probability, very likely to become profitable. And the red ones are actually very likely to become unprofitable. And you get offered an investment opportunity that is characterized by a combination of x1 and x2. Yeah, so it might be the liquidity or the solvability of a company, for instance. Yeah, so there might be two numbers characterizing the investment opportunity. So a normal neural network will simply tell you it's red or it's blue. The Bayesian neural network will actually tell you, well, it's blue, but it's in a high uncertain area with high uncertainty. Yeah, so the model here actually has a high standard deviation in its prediction of the probability that it's a good investment opportunity. Yeah, so that's additional information that you do not get from a standard neural network. So you may either decide that if it's characterized as profitable on average, but there is a high standard deviation, you may still want to decide not to invest in this investment opportunity. Or alternatively, if you get investment opportunities that are here in these darker areas, you may want to take a bit more time to investigate the investment opportunity. Yeah, because the Bayesian neural network has actually given you a sense that although the prediction is it's a profitable investment, we also know that for different draws of the posterior, we actually get different predictions. That it might actually be not a very good investment. So that's the value added of doing the neural network in a Bayesian way.